Hi, welcome to es301 Engineering Analysis. This is chapter 15 on constrained optimization. Here are the learning goals. At the end of this, you'll understand what constrained optimization means. You'll qualitatively understand a graphical method for solving a two-parameter optimization problem. You'll know how to use slack variables to transform constraints into linear algebraic equations. You'll be able to numerically solve the constrained optimization problem with arbitrary parameters and constraints. And you will also know how to use Excel to solve an optimization problem. So let's describe what is constrained optimization. And the best way to do it is, I think, from just like an example. So imagine what I wanted to do, what I wanted to optimize. What I want to do is I want to maximize. I want to optimize my profit. So I want to maximize my profit and then there might be some list of constraints, things that you have to abide by. So for example, you may only be able to work 40 hours a week. You may only be able to have a certain amount of material, maybe a certain amount of packaging, and then you're going to produce two different products, right? You're going to call them widgets 1 and widgets 2 that you can sell for $30 and $40. All right, so what I want to maximize is my profit. And so my profit, as I realize, is going to be, well, $30 times the number of widget 1s that I have. So I'll call that W1 times 30, plus the number of widgets that I have, W2 times 40. I want to make P as large as possible. All right? But I've got these other constraints, these other three things here that I also need to abide by. So I can't just make 1 gazillion widgets 1 and 1 gazillion widgets 2. I've got to go ahead and abide by these constraints. And that's the difference between what we did before, which was unconstrained optimization, where we let the variables take values from minus infinity to positive infinity. All right, so let's go ahead and look at each one of these constraints. We just said that the constraint says that, for example, W1 takes 2 hours and widget 2 takes 3 hours to make. And we know we can only work 40 hours per week. So what that means is if I take, my constraint would be 2 times W1 plus 3 times W2, and I know that that needs to be less than or equal to 40, because this first one here is the number of hours it takes to make all my widgets 1. This is all the numbers of widgets 2, and that right there has to be less than or equal to 40. So I can go through and do each one of my constraints, and I realize it's fairly straightforward. Here I'm going to have 1.5 times widget 1 plus 1 times widget 2, and that's going to be less than or equal to 25. And let's look at our third constraint in terms of packaging. And there we have 3 times widget 1 plus 4 times widget 2, and that's going to be less than or equal to 100. Now, another thing to notice, there can be any number of constraints. As long as there's one constraint, it's considered constrained optimization. Usually, you're going to have more constraints than you have parameters. Here I have 2 parameters, widgets 1 and widgets 2. If you have less than that, it turns out often there is no optimum, and it might just be infinity. All right, so let's first describe the graphical solution, and this helps to understand what we're doing when we go to the numeric solution. So let's go ahead and stick with that example that I started with, which was this idea of widgets. And I've written my 3 constraints up here at the top. And what I'm going to do is now I'm going to go ahead and plot this on this XY graph, or essentially a widget 1 versus widget 2. And I'll plot each one of these constraints to know where the parameter space is, or the solution space is, that would solve this. So let's make each one of these lines 5, so 5, 10, that would be 15, and 20. I'll do the same on the bottom, 5, 10, 15, 20, and 25. So let's go ahead and look at our first constraint, which says 2 widgets and 3 widgets has to be less than or equal to 40. And so this is a linear equation, linear in widget 1 and widget 2. And when I realized what I could do is I could make just widget 1, I could make 20 of those, or I could go ahead and make, well, 40 over 3, which is 13.3. I could go ahead and make that many widgets 2. Or some linear combination of the two. And so what that's going to do is it's going to create a line that looks like this. And if it needs to be less than or equal to 40, anything to the left of this line, left from the bottom, is a valid solution. I would go ahead and satisfy that constraint. So let's go ahead and do our next 3. The next 3 right over here I've got is this 1.5 times widget 1 and 1 widget 2. So what that means is 1.5 over 25 to figure out my x-intercept, and that's going to be right over here at 16.6. So if I did just widget 1, I would be there. And then the other intercept would just be 25 over 1 right there. And so I can go ahead or do some linear combination. It would look like this. Oops, my line didn't quite line up. Perfect. And again, I need to be less than or equal to that, so I'm going to be somewhere down below. So what I realize now is like my solution space is now this lower left-hand corner to become reduced. Let's go ahead and keep adding our other constraints. Our third constraint over here says that I can only have maybe 33.3 of widget 1 or 25 widget 2, and that constraint would look like this right here, less than or equal to the left. So what I realize is actually a redundant constraint because I've already constrained myself to the lower left, so clearly I'm going to need that third constraint. So now if I want to go ahead and figure out what my maximum is and my optimum, now I need to consider the profit, which is how much I make from each widget. So for example, let's say I made 5 widgets of 1 and no widgets 2, that would give me $150. And so if I wanted to make $150 making just widgets 2, I would make about a little over 3, and so I would have a line right over here which would be effectively my $150 line. And so each one of my profits, if I was to increase this, I could go ahead and make some number here, and this each time is going to increase my profit. And I realize the line that's going to maximize my profit is going to be the one which intersects these two lines here, or effectively the first two constraints. If I set them equal to 0, and go ahead and solve it, that's going to go ahead and give me what my solution is. And if I do that, W1 is equal to 14, W2 is equal to 4, and that's going to be my maximum. It's going to be this point here. And this third one over here, this third constraint, I didn't have to meet. And in fact, I met it, but I went ahead and had an excess or slack. And so, for example, if I put my values of 14 and 4 into that equation, what I'd find out is I've got an excess of 58. And that's what we're going to be calling slack here in a minute, which means I've got some slack in this equation. This one actually remains an inequality. It's actually 58, and it is less than or equal to 100. All right, so first, before we go ahead and look at the numeric solution, I just want to mention a couple caveats that can happen. This can happen with a lot of numeric solutions. First example here is a picture from the textbook. It's sort of what we just looked at here, where our solution space is over here in the lower left-hand side. This dotted line might be my optimization. And so I realize that my optimum is going to be that point there, similar to what we just did. But there could be a case where my constraints don't give me any possible solutions. So these little arrows here are showing what the constraint is. And here I've got somewhere, for example, x1 and x2 need to be larger than some value. And so what I'm looking at is for areas that satisfy all of these. Well, this one satisfies 2 of the constraints, but not the third one. Over here in the negative space, if that was even a possible parameter, would maybe satisfy these 2, but not this one. So clearly there's no solution, so there would be 0 solutions in that case. You could also set up a case where your solution space is infinitely large. And so what you realize is this whole area down here, which goes all the way out to x1 is equal to infinity. And in fact, it's actually, in theory, goes up to x2 is infinity. If this is increasing profit, there's no unique solution to that. I could find infinite profit by producing infinite x1s and x2s. And so here's anything where there's not a single unique solution. The middle case there with 0 solutions. And so those are some caveats, and what you need to realize is you won't be able to solve the numeric problem if you have a problem set up this way. All right, so now I'm going to go ahead and look at doing numerical solution. And this introduces this idea of slack variable. And so, as I mentioned before in that previous example, one of those constraints, we had some slack or some addition in it. And so I could turn those inequalities into equalities by writing the equation 2w1, this is that first one I had, plus 3w2, and that needed to be less than or equal to 40. So I could do is I could just say, well, there's some non-zero or possibly 0 value s1. So I'm saying that s1 is going to be greater than or equal to 0. It's the slack that I have. And so if I write down all 3 of my equations, I'm turning inequalities into linear equations. This is my second equation, plus 1 w2, and the slack in 2 is now equal to 25. So notice I'm turning inequalities into equalities, and the third one was, oops, the third one over here, which is 3w1 plus 4w2, and then there's a slack possibly in the third one, which in our case turned out to be the case. It was this one right over here was 58. And it turned out that over there, S1 was equal to S2, which was equal to 0. So it had the equal 0 option. And so this is how we're going to go ahead and solve our problem, because by now we're setting up linear equality equations that we can go ahead and solve numerically. Okay, so what I'm going to do is I'm going to use the textbook example, because I'm going to solve it somewhat differently. And that way you have both the textbook example and then my, or the textbook technique as well as my technique. So we're going to solve the same problem. It helps to draw analogies between the two. So if you haven't read the textbook yet, you should go ahead and do that now. And so this is that problem where we're producing two different products, a regular and a premium fuel. And there's a certain amount of raw gas that goes in. That's one constraint, the time constraint, and a storage constraint. And then here's our profit equation. And the notation they use is they call this X1 and X2. So we'll go ahead and stick with that. So for example, this first one right over here, which says regular or X1 takes 7, and the premium takes 11, and our total resource is 77. That our constraint would be 7x1 plus 11x2 has to be less than or equal to 77. And so there ends up being 3 different constraints in this problem. So actually there's 4 because these is the amount of regular and premium that I can have. Okay, so if I go ahead and introduce slack variables and then write those 4 equations that I have this way, what you realize is it starts to look like a matrix where I've done this spacing such that you can clearly see I've got my values of x1, x2, s1, s2, s3, and s4. And so what I have is I have 6 unknowns as I have it written, and I have 4 equations. And so clearly I can't solve this. I would need to go ahead and reduce the number of equations that I have by 2. And so that's what we're going to do. We're going to look at doing it. Now, as I say, I do this a little differently than the book, but we end up with the same result. Okay. So let's look at it. This is our matrix on the left-hand side. Now I just have the coefficients. I'm going to be multiplying this by a vector. I didn't put my vector down here in the middle because I don't know what it is yet. And then this is the solution column over here on the far right. Okay. So what I need to do is I need to get rid of 2 of these equations. And effectively, by getting rid of the equations, I am making a specification. Instead of solving for the variable, I'm going to specify what it is. So for example, I might specify that some slack variable is going to be equal to 0. I need to determine which ones I need to do, and I need to do 2. So effectively, I'm removing 2 of these columns, 2 of these slack. So I'm going to write the variable names above it, x1, x2, s1, s2, s3, s4. I'm writing them up here because we're going to go ahead and get rid of some of them, but to remember which ones they are. Okay. So what I want to do is I want to figure out which one of these slack variables I can get rid of. Now, if I start off with a simple solution that says x1 is x2 is 0, that would get rid of these first 2 equations. I'm making a specification. I would solve this simple identity matrix, s1, s2, s3, s4. The value of that would hopefully be 77, 80, 9, and 6. And so now what I'm going to do is I'm going to get rid of one of these columns and introduce one of these other ones. And that's what the book calls an entering variable and a leading variable. So for example, we're going to go ahead and say, well, we want to produce a finite amount of x1. And so if I was to do that, so now I'm going to solve for x1, which means I'm going to specify things, for example, equal to 0. So if I was to specify s1 is equal to 0, how many x1s could I make? Well, if this was 0, I realized that I could make 11 x1s. If instead I specified s2 to be 0, I could make 8 of x1. And then if I was to go ahead and specify s3 to be 0, I would be able to make 9 of that. And so clearly, 11 would be the largest value, and I want to maximize profit. You see our profit equation here in the bottom, and so it increases with the number of x1. So I would like to go ahead and make that as large as possible. So I'm going to get rid of that column, and I'm going to introduce x1. All right. So now let's look at what we want to do is we're going to get rid of one more slack. So we're going to look at x2. We don't need to look at s1. We already know we're going to go ahead and get rid of that one. So let's look at it. If I was to set s2 equal to 0, well, if I was to set s2 equal to 0, I realized that I could go ahead and make 10 of x2. And if I was to look at this bottom one right over here, if I was to go ahead and set s4 is equal to 0, I could make 6 of s2. So clearly I'd rather make 10 than 6, so I'm going to go ahead and get rid of that column. So now I have these 4 columns left, and now I can go ahead and solve it. So what I'm effectively doing, I'm specifying that s1 is equal to s2 is 0, and I'm going to go ahead and solve these last 4 equations using my 4 constraint equations. Okay. So this is what the matrix looks like. I got rid of those 2 columns. Now I went ahead and filled in my variables because I know what they are, x1, x2, s3, and s4. And I'm just going to go ahead and solve this. And so you can use any numeric routine that you want. The book mentions using, for example, Gauss-Seidel. I'm just going to go ahead and do this quickly in MATLAB to show you how you can do this. So here is the solution. I've specified my matrix A and B, and then I just went ahead and solved it. And so what I realized up in the top, that right there is x1. Next one is x2. This is S3, and this is S4. Let me quickly mention, I'm pretty sure the version of the textbook that you have actually flipped x1 and x2 just when they described it. So be a little careful. You don't want to go ahead and verify the solution. I think they have x1 and x2 flipped. Okay, so there's the solution that I have. I've set S1 and S2 is equal to 0. I now solve for slack. Here's my slack in 3 and 4. And so this is my point graphically that effectively I did, right? And so there's the slack in S3. There, right there, is the slack in S4. And you realize there is no slack between S1 and S2. So hopefully you get an idea of what's going on graphically when we go ahead and solve this problem. Now, once you have more than 2 parameters, it's a little difficult to do graphically. So it's a lot easier to do numerically. All right, last thing I want to do is I want to go ahead and do an Excel example. We'll go ahead and solve the exact same problem. So let's go ahead and go to Excel. All right, so I've set up this same problem in Excel. And so let's go ahead and look at what I have. I've got my values of x1 and x2 that I'm solving for. And I just set those equal to 0. And then I went ahead and put in my profit equation, which was 150 of x1, 175 of x2. And these are my constraints, which are also dependent on x1 and x2. There's the one for material. Right there's the one for time. Here's the one for storage of x1 and the one for storage of x2. And then these numbers below it, I just went ahead and entered exactly what the constraint values were that they need to be less than or equal to. All right. So now we'll go ahead and do an optimization. What we want to do is we want to optimize our profits. We want to optimize cell C2. So in order to do this, go to your Data tab and then go over to Solver. If you do not have the solver, if you do not see the solver on there, what you want to do is you want to go under File, and then you want to go under Options, and you want to look at your add-ins, and then manage your Excel add-ins. Go ahead and click Go there, and you want to click this Solver add-in button. Okay, if you don't have the solver. So if you don't see solver on your tab in Excel, go ahead and just install it there. Once you've installed it once, it'll stay in there. Just go ahead and click on our solver, and so if we look at it here. Set the objective. That's what we want to do. So my objective is I want to maximize profit. So I'm going to go ahead and select that cell. I'm going to click the radio button to maximize. And then what cells do I want to change? Well, I can change 2 cells, so x1 and x2. So I'm going to go ahead and change those. And now I'm going to add constraints. So what I want to do is I'm going to click the Add button. It's going to give me a new little window. And so the reference, I'm going to go ahead and say, well, here's one constraint. This value, which is in D2, has to be less than or equal to, and I'll go ahead and just put in that value, the cell right below it, which is D3. And we can go ahead and just keep adding our constraints. So I'm going to go ahead and add all 4 of my constraints now. Okay, I've added my 4 constraints. Each one of those had to be less than or equal to some value. You can go ahead and change your solving method. I have it right now set down to this simplex method. Actually, any of those will actually work, but since we're doing a linear problem, that will work. And then you should be able to go ahead and click Solve. And so now we have our answer. It asks you whether it wants to keep the solver solution, which just means keep it in the cells that you have. I'll click OK. And so now we look at our answer here. And this is exactly what we saw in the textbook and in the example we just did, for our optimum values of x1 and x2 and our maximum value of profit. One of the things about Excel is you can do nonlinear equations as well as linear equations. So which means all of these constraints, for example, or even my profit equation doesn't need to be linear in x1 and x2. It's a little bit more robust. When you get to nonlinear ones, sometimes it doesn't converge, but that's a little beyond what we need to talk about in this class so far. So we'll go ahead and just leave it at that. Okay, so let's go ahead and review what we talked about. We saw that constrained optimization effectively limits the search space for your possible solutions. Just because you have constraints, it doesn't guarantee you're going to have a single solution. You could have no solution or an infinite number of solutions. The graphical solution technique for the 2-parameter problem helps visualize how optimization works. So it's kind of nice to understand what's going on, but as soon as you get more than 2 parameters, it's difficult or impossible to do graphically. The numerical solution of this constrained optimization problem can be accomplished by essentially transforming it into a matrix math problem. And then last, we saw that Excel is one of many numerical packages that can perform constrained optimization, and also it can do both linear and nonlinear optimization.